And we've got other things in here. And the interesting thing is when we look at the trace elements, this is like a spider plot. Won't worry too much about it. We should get on. But so the quartz monzonite plot's there. That's obviously a felsic one. These are a little bit more intermediate. Then we go, there's our lampriphiers plotting there. There's our spessartine lampriphire. These are ultramafic rocks are plotting there. Our diorite is plotting there. Our granite porphyry dike is plotting there. And whoops. And when we put them all over each other, so everything, it's the most amazing thing I've ever seen this. All the trace elements, it must mean that they're diffusing through the system effectively. The whole thing is sort of coming to an equilibrium, despite the fact we've got these lampriphiers, the ultramafic lampriphiers, right through to granites. And also, when we look at the clinopyroxenes, so this is a magnesium, should be Mg number. That's the ratio of MgO over MgO plus FeO. So these things up here are very magnesium, they're mantle type signatures. We can see the rock itself has got very high magnesium numbers. So I think we've got some things coming in here. We've got high magnesium numbers for a granite, for example. And then when we look at our clinopyroxenes, we've got, these are our late ones. These are the xenocrysts in here. These clinopyroxenes are the sort of thing that people use as indicator minerals for diamonds in kimberlites. So these are coming from the mantle down in here, and these things here are mantle crustal mixed signatures. Yeah. So very, very unusual rocks. Never seen anything like this anywhere around. And these intrusion-related deposits are rare. So unusual minerals, strange textures. What does it mean? And probably it means we've got a complex magma system with evidence for mantle and crustal input. The mafic component is alkalic. It's volatile rich that's sourced from enriched mantle. It's sort of lampropheric. Lots of evidence for mixing, quenching, and volatile solution. Could just put the things, myrolitic cavities, CO2, calcite in there. So we've got CO2 as a volatile component. So if we try and put this all together into a model, so we've got deformed rocks, they've already been deformed. We get a little bit of extension. We get some felsic magma coming in. As we go on, we get intermediate magmas, and finally all these lampriphiers coming into the system. And if we try and make a model that explains all this, so it's post-collision and subduction. So do the first thing. So we're getting this extension, the stenospheric heating, something like that. The metasomatized lithosphere starts to melt. We get all these lampriphiers. They melt the bottom of the crust. We get lots of diffusion across that boundary, particularly of volatiles. Then we get the intrusion of the granitic material because it's less dense. So this stuff is less dense than that, so this actually can't intrude till all this stuff gets out of the way. And then we get more and more felsic rocks, and finally we get the lampriphiers and so on coming right through the system. So we've effectively got a deep mantle source, which is probably full of gold and other elements, potassium and so on, coming up with CO2-rich fluids, forming these granites. These are coming up, and then we're getting mineralisation in the tops of these granites. We're probably getting reduced carbon from the sedimentary sequence. We might be having tin and so on from the crustal melts down in here, and we're probably getting our gold actually from the deep lithospheric mantle, which is where I think the orogenic gold probably comes from as well, but via a different mechanism. Yeah.
This gold telluride, are they travelling in gas?
We don't know how they're travelling. The lampriphiers are often quite enriched in gold, like, you know, ones Nick Rock looked at might have 20, 40 parts per billion, not 1 part per billion, and they're enriched in these things. So I suspect they're coming up in the lamprifier as a part of a melt phase. They're going off into the CO2 rich fluid, and they're actually infiltrating into the granite. So we're pumping this stuff into the granite. Then the granite intrudes, comes up to a particular level, and because we've now got a CO2 rich fluid with methane in it probably, it actually exsolves at a deep level. It doesn't come right to the surface to exsolve. It exsolves at 8 kilometres or 6 kilometres, because we haven't got a saline fluid now. We've got a fluid that's absolutely enriched in CO2 because the CO2 is being transferred. That's the sort of model, but we don't know because it's something that's so deep. It's the same problem. But it must be something like that because this lampripheric association is so strong. And all of the chemistry will tell us we've got this sort of a system going on. So I'd say gold in the lamprifier, probably tellurium in the lamprifier. That's coming up into it going via a CO2 rich fluid in here. CO2, probably methane coming from the sediments along the side here, and probably arsenic and other things coming into the system, comes up here and effectively boils or phase separates at a deep level. That would be what we think. So, continental margin inboard of a magmatic arc, so we need evidence of continental crust. That's why I was asking you, where are these old rocks in Egypt? Post-collisional, commonly following a cessation of subduction. The magmatism is very, very unusual, so we should be able to pick this up. The hydrothermal activity is around the Pluton, so we get a diversity of mineralisation styles with zoning, and the fluids look like orogenic fluids. They've got low salinity, they've got CO2 and so on, because the fluid is exolved. Because of the higher vapour pressure of the CO2 and methane, the fluid is exsolving before we get to the fractionation and form saline fluid, basically. That's why we don't get any copper and other things in here. We could leave it at that, and perhaps I'll just show a couple of aeromagnetic images of what it looks like, and then we'll call it a day. Everyone's getting tired down the front here, I can see. So I'll just show you a couple of images, and then we'll give up. So, in case people have seen these things, it's quite interesting. I've seen these things in Mali. So, you know, we won't worry, it's just about exploration, we won't worry too much about it. One of the interesting things you can see, this is arsenic, they're very clear centres. So you don't get it all the way around the belts, you actually get discrete centres because these things are around individual plutons. So, very high. Yeah, I can give you some numbers, but I can't remember them offhand. But for example, the water supply in Fairbanks, right, USGS have been quite worried environmentally. The natural water supply in Fairbanks is something more than 10 times World Health Organization absolute maximum levels, you see. So I always think, you know, did the crazy people go to Alaska? Or are they crazy because they went to Alaska? You know, because all these towns must be full of this arsenic rich. All the towns near these plutons are full of arsenic. Yeah, yeah. If you went to Fairbanks, you'd just drink beer or Coke. You'd never drink water. So it's very high. This is what the geophysics looks like. Now the plutons themselves are reduced. They don't have magnetite, so they have negative. They have a negative signature. But because there's pyrite, these are shelf sediment. They're normal sediments forming in a shelf environment. They've got lots of framboidal pyrite in them.